As promised, we're back. Anyway, we're discussing technology node scaling, and basically this figure shows that the technologies are shrinking as time is going by. In the earlier days, it was 350 nanometers, 180 nanometers, 90 nanometers, 65 nanometers. Roughly now we're sitting down around here at about a 20 nanometer node technology, and that's related to the size at which you can make a transistor or something on that order. So basically you should take a look up and see what technology node means. It may not be all that clear, but it's definitely related to the size at which you can make a device. Here's some of the associated problems with technology scaling. It's sort of an overlay of the previous slide. It indicates there's some lithography challenge. Those are challenges related to making the chip, and others are technology challenges, and those are related to the chip itself, like the performance, getting the speed up, leakage power, and active power. That's basically, the power that's dissipated while you charge and discharge capacitors at a high rate. This figure here sort of shows why some of the technology has shrunk in size, and it's often related to materials processing and improvements in that area, or lithography enablers, which basically allow you to make smaller or finer resolution masks. So up at the top here you see there's sort of tungsten plugs between the metal layers, and that coupled with mechanical planarization allowed you to make a large number of metal layers when you interconnect the chip. Some of the other improvements down here are the high K dielectrics. Those are dielectric with a very high dielectric constant, which allows you basically to put more charge into the channel. Some of the examples here from that technology roadmap are related to challenges that the industry sees, and here for example is a section of a table that I took from DRAM technology requirements. It's interesting to note in some cases they have solutions that exist that are being optimized, others they know there are solutions, and others they don't have solutions that exist. And for example, when it looks at the DRAM cell FET structure, it sort of indicates that their manufactural solutions in 2012 will be a FinFET, and after that it goes to a VCT. I'm not even sure what VCT means. It might even mean voltage challenge transistor. I'm sure that's not it, but in any event, you can also see there's sort of areas in red here that indicate that they don't really have solutions for scaling the technology in that direction yet. With respect to technology scaling, of course, the cost per bit, if it's RAM, has gone way down. The cost for a transistor and a logic circuit has gone way down. But the other side of that, the capital cost to invest to produce these chips has gone up tremendously. It sort of points out that if you wanted to build a fab facility now, it's going to cost you about $5 billion. So anyway, resulting from this, the manufacturing and R&D costs of a fab facility, many companies are turning fabless. So they focus on design, and that's something that we'll also do here, so it works out well. Once a design is completed, they're contracted out to one of the few remaining microelectronics fabrication facilities, or in many other cases, there are lots of ASICs that are built now as field programmable gate arrays, sort of removing the foundry to the desktop. Here's just a picture of some transistors that scaled from 2001 to about 2009. You can see up in 2001 it sort of looks like our old friend the transistor, and it sort of starts looking like something that doesn't even resemble a transistor anymore. And these are the technology nodes below that: 130 nanometer, 65, 45, and 32. And there's an in-class assignment that basically asks you what are these pictures of. This is a schematic of what each of these would look like. Here's an example that is probably showing off the technology more than anything, where they have I guess this would be like a scanning or transmission electron microscope kind of picture of a very thin oxide layer that was created between a piece of polysilicon and a piece of silicon. It's only 12 angstroms, so you wouldn't see that in a chip nowadays. It's more likely to see maybe a 50 angstrom oxide layer, and it would basically be sitting there between the gate and the channel of our old friend the MOS transistor. In any event, it does appear that when you start making things this size, you're going to start running out of atoms when you have to dope them and make them either P or N type. Here's a little picture with respect to technology scaling, where it indicates that power dissipation could be a problem. This to sort of put some processors in perspective with a hot plate, and this is power density, so it's watts per square centimeter. Nuclear reactor, rocket nozzle, or the sun's surface. And here's some a picture of some processors that are overlaid on that. You can sort of see where the hot plate is, and the Pentium Pro, Pentium 2, Pentium 3, and up here nuclear reactor. So the power dissipation is actually becoming quite significant, where you're trying to remove, upwards of 20, 30, 40, 100 watts per square centimeter. And that's very difficult to do. So as a consequence, often you look into a computer, you see pretty massive heat sinks and sometimes liquid cooling, just to try to keep the heat under control. Here's an example of a graphics card and sort of the power requirements. So for these, I think, were NVIDIA graphics cards. This points out that you need on the order of 500 watts to operate these cards. This figure here to sort of illustrate some of the device changes that have to happen if you wanted to scale them down and try to make smaller and smaller devices. They're not always obvious or easy to do, but you can sort of see what the consequences are of an ideal scaling kind of environment. Here you have to scale the voltage by lambda. You have to scale the oxides by lambda, very difficult to do. Voltage isn't that easy to do. It's always guided by standards and whatnot. The wire widths are scaled by lambda, gate length width are scaled by lambda, and some of the materials properties are also scaled by lambda. An increase in doping concentration in the substrate, and a decrease in the dimension that is associated with the diffusion region. But some of the results are that you do get a higher density, lambda squared, higher speed going up by lambda, and lower power per circuit, 1 over lambda squared. And that's kind of related to the V squared over R kind of power dissipation that you'd expect. So as a consequence, the power density is approximately constant, unless you want speed, in which case the power happens to also go up. So an in-class assignment, why is power density approximately constant? And that should be relatively straightforward to figure out. So some of the integrated circuit families you may have seen in the past are used to implement a VLSI or an ASIC or an SOC electronic circuit. Different logic families are emitter couple logic, transistor logic, integrated injection logic, metal oxide semiconductor, the MOSFET, NFET, and PFET, and our complementary metal oxide semiconductor, which is both N and P type. So that's CMOS, and it's basically the Death Star for all the others. Each technology has its own features. Some maybe are better cost, performance, design time, advantages and disadvantages. Maybe some bipolar technologies are so useful, where very high speed and you have the power to spend for it. But virtually all logic circuits are designed using CMOS technology, and that would be well into the high 90s, I'm sure. Time for a small break, and we'll be back.